Hello everybody and welcome back to another RevWise video. Today we'll be going through the IB Chemistry Higher Level Paper 1A Specimen paper. This is the multiple choice paper for the IB Chemistry New Syllabus First Exams 2025. I have not looked at any of the questions yet, so I'll just be going through them, explaining my thought process with you, and hopefully helping you guys get an understanding on how to answer each and every one of these questions. So let's get right into it. Question number 1. What is thin layer chromatography best used for separating? Well, this is just a pure theory question. There's no need for any critical thinking. We just know that it's A. It's used for molecules of varying polarity. Thin layer chromatography, that's what it's used for. If you're struggling to get it, I guess you could narrow it down by knowing that it's not C, because that's to do with metals in an alloy, and D is with water of crystallization, which has nothing to do with chromatography. And A and B are both about polarity and molecules, which are to do with chromatography. And then if you know about TLC, thin layer chromatography, you should know that the answer is A, varying polarity. Question number 2. Ice containing only this isotope of hydrogen sinks and does not melt when dropped into ordinary distilled water maintained at 3 degrees Celsius. Which statement is correct? Okay, let's just check all of them. So the isotope has a high natural abundance. Well, we know that's not true, and the reason we know it's not true is because if it had a high natural abundance, that means the relative atomic mass of hydrogen would be close to 2, because the mass of this isotope is 2. If it had a high abundance, the relative atomic mass would be close to 2. But if we check our periodic table, which we have access to from this paper 1, we can see that the relative atomic mass of hydrogen is 1.01. That's not close to 2, that's very close to 1, which means that the most abundant isotope must be the one with a mass of 1, and the one with a mass of 2 does not have a higher natural abundance, it has a low natural abundance, so that's wrong. B. Water with this isotope of hydrogen has a higher melting point than normal ice. And this looks like it should be correct, because it says it does not melt when dropped into ordinary distilled water at 3 degrees Celsius. And of course, we know that ice should melt at 0 degrees Celsius. So we know that's right. And let's just check the other two just to prove our answer, but we should know that B is right. This water has a lower density than normal ice-cold water. We know it doesn't have a lower density because it sinks. It has a higher density. And D, it has a different chemical properties. It's only a different isotope, so it's not going to have different chemical properties. So therefore, we know it's B. Okay, question number 3. This table lists successive ionization energies for an element Z. So we have this element Z, and yeah. So it's basically asking us for the formula of the stable oxide for element Z. So let's look at these different things. Well, it gives us the ionization energies. And what we're looking for here is a big jump. We're looking for a big jump between ionization energies, because that's going to tell us when the electrons are being lost from a different energy level. So let's see. This is a moderately sized jump, pretty normal. Similar sized jump, okay, normal. There we go. That's the big jump. So when we're losing it when we're going on the fourth ionization number, we can see it's a much bigger ionization energy. That means that this 4th electron is from a lower energy level, one that's closer to the nucleus. That also means that these 3 are all on the same energy level, and that there's, on the outermost energy level of our element Z, we have 3 electrons. That means our valence is 3, and that also means that the ion for Z is Z3+. There we go. So we know it's a 3+, and we know that our O is an O2-, because that's what O is. And then just to get the compound, we can use the easy drop-and swap method. I mean, of course, if you know how to just form the compound, it's very easy to figure out what it's going to be. But the drop-and swap method basically is where we move these numbers to the bottom. So it becomes Z2O3. So we've dropped them and swapped them. Z2O3, that's C, and that's our answer. There we go. Pretty easy first page. Question number 4. A container holds 30 grams of argon and 60 grams of neon. What's the ratio of numbers of atoms of argon to numbers of atoms of neon in the container? So it gives us the mass to start out with, but we can't just get a ratio from that. It's not just going to be 30 to 60 because that's not actually the atoms. What we're going to want to do is convert it into moles, because once we have moles, we can just use those moles as for the ratio, because to convert moles to atoms, we're essentially just multiplying by Avogadro's constant, so there's no need to convert it. We can just use the moles for our ratio. So how do we convert this mass to moles? Well, we just use mass over molar mass in order to get our answer. So let's just go to our data booklet and find our molar mass. So we have neon and argon here, and these are the two molar masses we need to be looking at. But you can see they're kind of not nice numbers, right? They're not really even numbers. They're not very round numbers. So it's kind of hard for us to do our calculations without a calculator. So let's just round them. So 20.18, that's roughly 20. And this is roughly 40. Okay. So now that we have that, our molar masses, we can just instantly start our calculations. So we know that it's 30 grams of argon over our molar mass of 40, and we have a ratio of that. This is the moles, by the way. So this is the moles of argon. Okay, is that okay? And then our moles of neon is going to be 60 over 20, okay? And that gives us a ratio of 3 over 4 to 3, sorry. 3 over 4 to 3. Now, from here, we're going to need to pick which one it is. And it's pretty clear that it's not going to be C or D, because we're looking at the ratio of argon to neon. And since we know that argon is less than neon, we can clearly see that argon's 3 over 4 to neon's 3. We know that the ratio of argon to neon is going to have to be a number that's less than 1. It's going to have to be a decimal like this. So which one's it going to be? Well, we can simplify this ratio to make it easier to see what the answer is. So first we can make this into 3 to 12, because we're just multiplying everything by 4, and then we can simplify this to 1 to 4, and that's the same as saying this, 1 over 4, that's just going to be 0.25, which is A. Very easily done. Now question number 5. This looks like it might be a bit more challenging. A gas storage tank of fixed volume V contains N molecules of an ideal gas at 300 Kelvin with a pressure of 40 kilopascals. Now N over 4 molecules are removed, okay, and the temperature is changed to 450 Kelvin. What is the new pressure of the gas in kPa? Okay, so before we think about like even substituting our values in, let's just get a rough equation going, rough couple equations going, just so we know what we're working with. So we're looking at the new pressure difference. We're going to have a P1 and P2, okay? And we know that the volume is remaining constant. So we have this P1V equals 2, and we have N molecules, but the molecules are being removed, so we're going to have an N1 because it's being changed. And then we have nRT. PV equals nRT is the equation. You should know that, just the ideal gas equation. So then R, and then we have a T1 and T2 because the T is changing. So we have P1V equals 2 N1 R T1. That's the same as P2, not the same as, but it changes to P2V equals 2 N2 R T2. Okay, so now we have that. Now, of course, we can remove the constants when we're actually solving it, but we have a rough understanding of what we're going to have to do here. So now that we've seen these two, we can form a ratio from the two equations. And the easy way to do this is just by forming it into P2 over P1 equals to N2 T2 over N1 T1. And the way we've done this is by removing our constants here, the ones that are the same, and by forming a ratio between the other ones, the other parts, by dividing them by each other. So P2 over P1 equals N2 T2 over N1 T1. Now that we have this, we can just simply substitute everything from our question into here. So what do we have? We have 300 Kelvin, 40 kilopascals, and we have n over 4 molecules are removed. Don't get caught up on this. It's not actually n over 4. We're not dividing the molecules by 4. We're removing n over 4 molecules. So if we remove n over 4 molecules, we'll have 3n over 4 molecules left. 3 over 4 n molecules left. So that's kind of a trick they're using here. So if we substitute everything else, it's basically this P2 over P1 equals to 3n1 over 4 times by 450 for our temperature over n1, because that's the original, times 300. And then it's pretty clear to see we can split this up, split the fraction up, and if we actually split it up into the two fractions and simplify it out, we can see that these ends will cancel and we'll get 3 over 4 times this part, 450 over 300, okay? And if you can see how this simplifies, you'll see that it equals to 3 over 4 times 3 over 2, yeah? And now that we have 3 over 4 over 3 over 2, we know that's going to be 9 over 8. Okay, so we have 9 over 8, and we have our P2 over P1. So we have 9 over 8, so we have equals to 9 over 8. And our P2 over P1, well, we know P2 is what we're trying to find out. We know our P1 is 40 kilopascals, so over 40. Then all we need to do is multiply these sides, and we get P2 equals to 45. P2 equals to 45. There we go. That's C. So pretty simple, just required a bit of working on. I think, yeah, just a standard ideal gas question. Question 6. What is the formula of the compound formed by magnesium ions and hydrogen carbonate ions? This is just, yeah, we know we have Mg2 plus, and that's why it's going to require 2 of the HCO3, because it's HCO3 minus, it's that, right? So we're gonna need to make it 2, and then this is gonna have to be Mg, so it's gonna be B. Yeah, a very easy question. Free mark. In which group of ions and molecules are electrons delocalized in all species? Okay, interesting. So, okay, let's just go through one by one, I guess. So instantly, before I even go to A, I know that I can eliminate C because it has diamond, and that does not have electrons delocalized. Okay, then for A, we have CH3COOH, and we know that doesn't have delocalized electrons, if you can see how I'm drawing it. This double bond doesn't actually show resonance. It's just a double bond because this O is connected to a H. It's in a different environment than this O, so we can't actually resonate to this double bond like that. That's not possible. So this actually does not have delocalized electrons. So we know it's not going to be A either. So we know it's not A. We know it's not C. What about B? So we know graphite, yeah, that works. CH3COO minus, well, if we have a look at that, if you're wondering, I'm not drawing the hydrogens, it's a tip for your paper 1. If you're drawing a bigger organic molecule, I don't think it's worth it to really think about your drawings. You're just using it to help yourself understand or visualize the question. So just draw your structures really quickly as long as you can understand them. That's why I'm not drawing the hydrogens. So we have CH3COO, and you can see these O's are in the same environment. Previously we had an OH here, and this H made it different, but these two are the same now, which means that this can show resonance. We can have resonance. So this is electrons delocalized, yes, and NO2 minus, well, we should know the structure for that just regularly, but yes, this can also show resonance. So yep, it's B, okay? And we know D is not right because, well, C2H4, yeah, we don't have anything there. So B is correct. Just draw it out. If you're struggling to do it, just draw it out. There's no point stressing about it, really like worrying, just draw it out. Okay, what is molecular geometry of central atom in SF4Cl2? Yeah, I'll follow my advice. I'll just draw it out. So SF4. Remember, S can sulfur expanded octet. That's why we're able to do this Cl2. This works. You can see there's 1, 2, 3, 4, 5, 6 electron domains. So we know it's not linear, not tetrahedral, not hexagonal is not even a thing. It's octahedral. There we go. Okay, 9. Which is the preferred Lewis formula of nitrous oxide as induced by formal charges? Okay, so for formal charges, we know that we're essentially taking the valence electrons, subtracting these non-bonding electrons, and then subtracting the bonding electrons, and that gives us the formal charge. So let's just calculate it for each of the atoms. We're looking for the lowest formal charges, which would be the preferred Lewis formula. So let's check A. So nitrogen has a valence of 5, and then we can see there's 1, 2, 3, 4 non-bonding and 1, 2 bonding electrons. So 5 minus 4 minus 2, that gives us minus 1. Okay, and I'm not going to write it out for the rest of them. I'm just going to do it in my head. So for the central one, we have 5 minus 4, and then, yeah, so it's plus 1. And our O is 6 minus 4 minus 2, and that's 0. So that looks pretty good already, but we have to check the other ones as well, because there might be a better one. So let's check the next one. We have 5 minus 2 minus 3, which is 0. We have 5 minus 4, which is plus 1. And then we have 6 minus 1, which is minus 1. So this looks similar, and I can already tell what they're going to be. Yeah, I can already tell what type of question this is. This is quite a difficult question, and if you get this, you really have to think about it, because these two look quite similar, right? They have both a minus 1 and plus 1. The formal charges do cancel out the minus 1 and plus 1, so you might be wondering how we can get it. So, interesting question. I'm just going to cancel out D. You can tell it's not going to be right. Firstly, just by your skills in multiple choice questions, you can see it looks different to all of the other ones, and you know that that's essentially the IB examiner telling you that this is not going to be the right one, and we can prove it's not the right one as well, but in the sake of time, I'm just going to tell you that this is not the correct Lewis formula. This is not how it looks like. The ends should be bonded to each other, which are then bonded to an O due to the electronegativities. Okay, now C. Let's check this. 5, okay, so this would be minus 2. This one would be plus 1 and plus 1. Okay, so let's eliminate C. We've already eliminated D. Eliminate C. Why? Because we can see this has the largest formal charges. We don't want high formal charges. We want low formal charge. We want it to be closest to 0. But what about A and B? They look pretty similar, right? You might think you're just guessing at this one because they look similar. But when you have something like this, you have to look at the negative charge. See, there's a rule for formal charges that many people don't know about. I'm going to write it here. When you have these formal charges, the negative formal charge, the negative formal charge is preferred to be on the most electronegative atom. Okay, that's the rule. So we're going to have to pick the most electronegative atom to place our negative formal charge on, and that's going to be the preferred species. So let's look at this. Now, which is more electronegative, O or N? Because here the negative is on the N, and here it's on the O. So which is more electronegative? Well, we're not able to look at the electronegativity because we don't have a data booklet, but we can look at our periodic table, and we should know that fluorine is the most electronegative, and electronegativity is increasing across the group, and we know that O is further across the group than nitrogen. So we know that O is going to have a higher electronegativity, So it's more electronegative, meaning that we are preferring it to have the negative formal charge, which means that we're going to take B. Nicely done. Okay, question number 10. Which pair of statements about electrons in this molecule is correct? I don't like these ones. They're quite annoying, but let's get counting. So number of non-bonding pairs of electrons. Let's just do that first because it's quite easy. Non-bonding pairs, where can we see them? Well, we see them in this O. There's one pair, two pair. In this O, there's one pair, two pair, and the N. This and this right here. Just one pair there. So it's going to be 5. So it's one of these two. And now electrons in pi bonds. So it says number of electrons here. And note that. It says pairs of electrons here, number of electrons here. They'll try and catch on this because they know that some people will not be looking at the number of electrons. They'll just be looking at the pairs. They'll be looking at just the number of bonds. So you have to make sure the number of electrons in pi bonds. Make sure you're counting the number of electrons. Let's find them. So we have a double bond here, right? So that's one pi bond, but that counts as 2 electrons because it's number of electrons in pi bonds. So remember, 2 electrons there. So we already have 2, and then we have this ring here. How many is there? Well, we know there's going to be 6 there because we have 3 pi bonds, and that's going to make 6 pi electrons. And if we add 2 plus 6, we get 8, and that gives us our answer of D. Nicely done. 11. What is the explanation for the malleability of metals? Very easy question. Bonds are strong? No. Bonds are weak? No. The bonds involve free electrons. That's not the explanation for the malleability. Bonds do not have a specific direction. Yeah, that's exactly it. Malleable, the ability to shape it. The bonds, the reason we have that ability to shape the metals is because the bonds don't have a specific direction. They're able to move in different directions. And yeah, there we go. Question number 12. Let's see. The structure shows the repeating unit of a polymer found in some plastics. Which monomer is used to form this plastic? So we know that when they show this, the polymer, they usually remove the double bond here, right? So we're just looking for what everything matches up there. So, I mean, I can just draw it out. We know there's going to be a double bond in the middle. I'm just going to draw it out. So CH2, CH3, CH3, 2. Oh, yeah, well, we found it. This matches up. You can see that the CH2 here, this is the same as my CH2 here. You can see this CH3CH3, this is the same as my CH3CH3. You can see there's a double bond here that was removed because this is a polymer. And yeah, you can tell that this isn't going to match up. This is also not going to match up. And yeah, you can draw them on if you want. I just think that it's not really worth your time because it's pretty clear that it is A because we drew it out. Okay, now question 13. Why is copper 2 sulfate blue? Now let's just read the options here. So red light is absorbed when electrons are promoted between the orbitals in the split d sublevels. Sounds about right, but let's just check the other ones. Blue light is emitted when electrons fall between the orbitals in the split d sublevels. Completely wrong. We know that electrons don't fall between the orbitals, and we know that blue light technically is not emitted. It is only shown as it is reflected as a consequence of red light being absorbed. Now, C, red light is absorbed when electrons fall between the orbitals. We know it's wrong because electrons are being promoted between the orbitals. They're not falling between the split d sublevels. Now, D, blue light is emitted when electrons are promoted between these sublevels. Now, common mistake is to think that, oh, blue light is here and blue light is in the question, so they must be related. No, blue light is not actually emitted. The blue color is observed because red light is absorbed, not because blue light is emitted. Because when we absorb a certain wavelength of color, we are reflecting the complementary wavelength of that color, and the complementary color of red light is around like cyan, like similar to blue, close to blue. That's how we're getting that blue color. Now, the fact that they're asking you this without you having access to your data booklet, quite a difficult question, but I think it should be able to be deduced because they only give you 2 colors, red and blue, and you know that blue light is not emitted, so it has to be A. So there we go. Now 14, which molecule has a carbonyl functional group? So carbonyl, I'm sure you know, is part of ketones and aldehydes, so we're looking for something like that. So we know it's not going to be D because we can see it has an NH2. We can tell C is an alcohol because it has that OH, so it's A or B. So let me just quickly draw out A to show you that it's not A, because you can see that A is this, which is not it. This is not a carbonyl functional group, so we know it's B. And if you want me to draw it B, I can just show you really quickly. There we go. Yeah. So this is our carbonyl functional group, the C double bond O. Yeah. Okay. 15. The block structure of the periodic table groups elements according to which characteristics? Okay. So block structure, we know our P block, S block, D block, those kind of blocks. So we're looking for something that relates to that. So we know it's not atomic number, that's not the block structure, that's just the order. Atomic mass, we know it's not that. Electron configuration, now that sounds about right, because P block, S block, that has to do with the electron configuration. But let's just check the last one, reactivity, that's false. So it's C, electron configuration. Yeah, pretty simple one, pretty easy to understand. Nice. 16. Which D block element has the highest number of different oxidation states? Okay, this I think is just useful knowledge to know. It's manganese, Mn. It has 7 if I'm not mistaken. Yeah, you should just remember that. Pretty easy to remember. It's even in your data booklet when you're not going to have your data booklet during this test, but when you're browsing your data booklet while revising, you should be able to see that manganese has the most oxidation states, so you should know it is manganese, Mn. So B is our answer. 17. What do all greenhouse gases have in common? A. They're all emitted by the burning of fossil fuels. Not true. What about methane being produced by cattle rearing? B. They absorb ultraviolet radiation. Not true. Not true for all greenhouse gases. They have symmetrical molecules they all are symmetrical molecules with no polar bonds. Also not true. And even if you wanted to check all the greenhouse gases you know to prove it, it'll be pretty easy to tell that they're not all symmetrical molecules with no polar bonds. And if you want to double confirm that this is not the right answer, we just look at D, and D is clearly the right answer because they do all absorb infrared radiation. That's about how the greenhouse gas occurs. Okay, 18. Which is the H1 NMR spectrum of cyclohexane? So what is cyclohexane? Well, you should know what it looks like, but I'll just draw it really quick so you can see it. There we go. There, 1, 2, 3, 4, 5, 6. Yeah. Sorry for the bit distorted drawing, but it'll work. That's what it looks like, and you can see that all the hydrogens. The hydrogens are here, by the way. I didn't draw them in, but you can tell where they are. They're all going to be in the same environment. So when we're looking at our peaks in our spectrum, there's only going to be one peak. And for this one, we have 2 peaks, 3 peaks, 4 peaks. We have loads of peaks here. We know it's going to be A because A only has 1 peak. We don't actually need to see what the chemical shift ppm is for each of them. We just need to know, look at how many different hydrogen environments are there and look at how many peaks there are, see if they correspond. And yeah, that was a pretty nice one, pretty easy to get. Okay, 19. We have a mass spectrum question. Which is the mass spectrum of butanol? Now, before we even think about answering this, let's just draw butanol. An aldehyde, 4-carbon aldehyde. It's going to look something like this. Okay, pretty simple structure. Now, we're going to have to find the mass spectrum. So how do we narrow it down? Well, the easiest way is by figuring out what the molar mass of butanol is, because then we can correspond it to the molecular ion. Essentially what I'm trying to do is look for the highest peak and see if the highest peak matches up to the molar mass of butanol, because the highest peak is just the molecular ion, which is essentially just the molar mass of the thing, the entire thing. So let's calculate it. So we have 4 C's, which is 12 times 4 is 48. Then we have 1, 2, 3, 4, 5, 6, 7, 8 H's plus 8, and then we have 16 from the O, and that should give us around 72. So we have 72, as our molar mass. So let's see if this has a peak of 72. We can see the highest point here is around just under 60. That can't be it. For this one, we can see, oh yeah, that looks like 72. This one looks also around 72. This one is no chance. Okay, so we've narrowed it down to two options. So how can we narrow it down more? Well, the easiest way is by simply breaking off small parts of it and checking if we can find a peak at the molar mass of that fragment. So you'll see what I mean when we start doing it. So what I'm going to do first is I'm going to just cut off this CH3. I'm going to just cut it off, remove it from this molecule, and we're left with this. Okay, so we're left with this, and we're going to want to calculate the molar mass of this and see if we can find a peak there. So how do we calculate the molar mass of that? We'll just remove this CH3 fragment. So CH3 has a molar mass of 15, so we're just subtracting 15 from 72. That gives us 57. So we have 57. We're looking for a peak at 57 for this fragment. So where can we find that fragment, molar mass of 57? That looks about right. Sorry, that's our eraser. Okay, there. That looks around 57. So, yeah, that works out. What about this one? Oh, it also has one around 57. Unfortunate for us because we have to do more, but it seems like they both match up. So what can we do now? Well, let's remove another CH2 from it. So let me just get my eraser. So we're gonna just do that, and we're going to remove this as well. So we're removing this whole thing. So we're removing a CH3CH2. So that's around a molar mass of 29, right? CH3CH2. So we're looking at this fragment now, the molar mass of this fragment. So it's 72 minus 25. That's around 43. Okay, so we have 43. We're looking for 43, and we can see if anything matches up to 43. So let's check this one first this time. So we can see this one at 45 exactly, but remember, we're looking for a peak at 43, and it's not like it's going to be fluctuating. It is going to be at 43 because this is the fragment, this is the peak at where we're removing this fragment of CH3CH2. This is this fragment, and it is 43. It can't be 45, so this is actually wrong. Okay, this peak at 45, it's wrong. Let's check this one, and this looks more like it. We have a peak at around just under 45, around 43. That looks about right. And just from that, we have confirmation that C is our right answer. That's how you work it out. You slowly want to keep removing more from the molecule, keep looking at the fragment size, the molar mass of the fragment, and then you can slowly work your way to the right answer. Okay, question 20. The potential energy profile for a coffee cup calorimetry experiment is shown. And it's asking us what is the correct interpretation for this reaction. Okay, so we can just see an exothermic reaction. So let's just cancel this. And we know that the temperature is going to increase because it's exothermic. So it's A. Yeah, I don't really know what to say to that. Very free marks. Yeah, that'll just be a 5-second answer. Okay, 21, enthalpy change question with Hess's law. Okay, let's just do it. So this is the final equation, and the best tip I can give you to do it is if you see an element or a compound that appears more than once in these three, don't mess with it. Just figure out the other ones first. If it appears more than once, it's more than 99% chance it'll just cancel itself out along the way or work itself out. So let's look at the things we need to do. So we need to get CO2 in the reactants. And where is CO2? Well, CO2 is here. Okay, so CO2 is currently in the product. So how do we make it in the reactants? Well, we need to flip it. We need to flip the sign, and that's going to involve making this a positive enthalpy change. So 566 positive. But you can also see that in this equation we only have 1 mole of CO2, whereas we have 2 moles in our equation over here. Okay, we need 1 mole only. So what are we going to do? We're going to half it. 566 divided by 2. That gives us 283. Okay, and now we're going to have to add 283 to what's next. So let's do H2 next. Where's H2? So H2 is over here, okay, in this equation. Okay, and we have 2 moles of H2. We only need 1 mole, so we're going to have to half it, but it looks like H2 is in the reactants where it should be, so we don't need to change the sign. So we're just going to keep the sign to negative, and we'll half minus 572. That should be minus 286. Okay, so then 283 plus minus 286, that's just going to be minus 3. So we have minus 3 plus something for our final thing. So for carbon monoxide, CO, we've already done that correctly because at the start we flipped this sign and then CO is here, and we already halved this enthalpy change. So we don't need to do anything to CO. Last is H2O. And you might be wondering what was happening here because H2O seems to be on the right side, but if you look closely, this is H2O gas. The product here is H2O liquid. We need H2O gas to be in the product. So what do? We flip the sign. So we have positive 44. So minus 3 plus 44, that's going to give us positive 41, and this other option, it is. So yeah, that's basically how you do Hess's law. Very easily done. Nice. Okay, which is a renewable energy source? Natural gas? Nope. Uranium? Nope. Coal? No. And wood? Yes, because we can grow wood. Very easy. 23. Which are endothermic processes in a Born-Haber cycle for the formation of an ionic compound? Okay, so it's endothermic processes. So enthalpy of atomization. Yes, very clear. It's an endothermic process. We need energy for it. Okay. First electron affinity. I'll skip that for now. First ionization energy. Yeah, it's very clear that first ionization energy, in order to remove an electron, we're going to need energy. Now, going back, first electron affinity, the reason I skipped over it is because it's false. Okay, first electron affinity, I skipped over it because it is an exothermic process and releases energy, not endothermic. You can make a case if it's a second electron affinity for being an endothermic process, but first electron affinity, it's going to be exothermic. That means that it's only I and triple I, which is going to be B. Okay, pretty easy. 24. What is correct as a system approaches equilibrium? Good question. So we know that A is just blatantly false. Our reaction quotient is not going to remain constant, okay? Our Kc increases. No, there's no reason to say it would increase. It's just approaching equilibrium, approaching our equilibrium constant. Delta G becomes more negative. Well, if you know your theory about equilibrium, you know that's false and that would also tell you that D is correct because it is that delta G approaches 0 because at equilibrium, delta G is 0 or Gibbs free energy. And yeah, that's just based on your knowledge. I think there's not really much you can do if you can't answer that one. Just need to study more. Okay, 25. The complete combustion of 20 centimeters cubed of a gaseous hydrocarbon CXHY produces 80 cm cubed of gaseous products. This volume reduces to 40 cm cubed when the water vapor present condenses. All volumes are measured at the same temperature and pressure. What is the molecular formula of the hydrocarbon? Wow, this is going to be a bit of work, but not too hard. So the way I would go about this is by using a formula. And it's one that you probably come across, but you might have thought that you don't actually have to memorize it. Well, technically you don't have to memorize it. It is very helpful to memorize it, and I really suggest you do memorize this formula. And it goes as such. So we have CXHY, okay? It is part of the formula, but it's also part of the question, so it just works out. So we have CXHY over here, okay? CXHY, and it's just a combustion reaction, but we're going to add things for the coefficients. So we have CXHY and then X plus Y over 4 O2. Okay, that's going to be the number for the O2 is going to be X plus Y over 4. And this works for any combustion reaction. Okay, this is the formula to how you can instantly balance the coefficients. Okay, that forms X CO2, okay, plus Y over 2 H2O. Okay, there we go. Now, from this, we can look at our volumes, okay? And the reason volumes are useful here is because the way volumes works with moles, you could just substitute volumes right into the equation because in order to get the volumes, we're just dividing it by constant, right? We're just changing it by constant. So there's no need to actually convert it into moles. We can just use our volumes. And our volumes are nice round numbers that are divisible by each other as well. So it makes it even more helpful. Now, it's telling us that it produces 80 cm cubed of gaseous products, but the volume reduces to 40 cm cubed when the water vapor present condenses. So when this H2O becomes a liquid, it's going to be 40 cm cubed of gas, which means the CO2 alone is 40 cm cubed. And what that allows us to do is say that X equals 40. Remember, we're just going to substitute the volumes for the moles here because there's no point making the numbers less round by actually converting it into moles. So let's just say X equals to 40, right? We have X equals 40. And from here, we're able to solve for Y because we can say that 40 plus Y over 2, which is going to be this one, this for the H2O, our moles of H2O, we know that 40 plus Y over 2 equals to our total gas. Remember, the total before the water vapor present, present condensed, the total was 80. So 40 plus Y over 2 equals 80. And if we solve for Y, we get Y equals to 80. Okay, Y equals 80. So now we know that X equals 40, Y equals 80, and we know that the complete combustion, we started with 20 cm cubed, okay? Now, if we make this a ratio, we can have this as 1 to 2 to 4, okay? So our X is essentially 2, our Y is essentially 4. And what this allows us to do is to just substitute our X and Y as C2H4 just by using ratios. That gives us C. Nice question. I think it can be a bit confusing, have to use ratios, but you have to recognize that you can just use these volumes as they are because that's essentially how volumes work. We're just, in order to convert it to moles, we're just simply changing it by constant, so there's no need to change it into moles. We can just use the volumes as they are, and we get C. Okay, 26, diagram shows the energy profile. Which combination is correct? So the activation energy of the forward reaction. So we know the activation energy of the forward reaction is this. It's this height, okay? So we're looking for that. So X is not right. Y minus X, that looks about right. There's two of them, okay? We know it's not Y, only Y either. It's going to be Y minus X. Now for the reverse reaction, it's going to be, I'll change the color so it's easier to see. It's going to be this, okay? That's going to be the reverse reaction. This little peak, and that's going to be Y minus C. Looks like it. Is there anything? Yes, we have Y minus C. So the answer is B. Easy question. Okay. 27. What is the main reason for an increase in rate of reaction when the temperature is raised? Very easy question. Let's see the options. A greater proportion of collisions are successful. That already looks correct, but let's see the rest. Particles collide more frequently, not necessarily the main reason for increase in a rate of reaction. We need a greater proportion of successful reactions, not just more frequent reactions. Bonds in the reactants are weakened, not true. The activation energy of the reaction decreases, not true. Activation energy is independent of temperature. So 27 is going to be A. A greater proportion of collisions are successful. There we go. 28. What is the equilibrium constant expression for the following reaction? Okay, so it's going to be Kc equals 2, and remember it's products first, so SO2, and then we put the coefficient as the exponent, so squared, and then multiplied by O2, all that over SO3, and coefficient is exponent squared. And is there anything else like that? Yeah, it's A. A matches with that. Very easy one again, pretty simple. Which statement is correct about points X and Y in the energy profile diagram? Okay, X is transition, Y is intermediate. No, in this case they are both transition states, and yeah, that's an option, option C. X and Y are both transition states. This is how they look, that's how transition states look like. Yeah, not really an explanation I can give. This is just, they are transition states. So yeah, nice. 30. The equation for reaction between two gases A and B, is A plus 2B forms C. It's a reversible reaction. And when the reaction is at equilibrium at 600 Kelvin, the concentrations of A, B, and C are 2, 1, and 2 moles respectively. What's the value of the equilibrium constant Kc at 600 Kelvin? Pardon. Okay, so let's just use the formula. Pretty simple. Yeah. So A, B, and C are 2, 1, and 2 respectively. So we know C has a concentration of 2 at equilibrium. So 2, and then let's just to make it easier for you to understand, I'm just going to write out the whole expression first. So it's going to be C squared over concentration of C squared over concentration of A times concentration of B squared. Just like the previous question, we're just using our Kc formula. Now let's sub into that. So it's going to be 2 squared over A is 2 times 1 squared, which is just 1. So it's going to be 4 over 2. It's going to be 2. So our answer is C. Nice question. Which reaction would be expected to have the largest Arrhenius factor, A, at constant temperature? Oh, wow. I would not expect them to give this question. But, yeah, I mean, pretty challenging question. Requires you to think. But, yeah, pretty solvable. So let's see. We have A, H plus I, hydrogen plus iodine forms HI. Yeah, pretty decent contender, pretty simple reaction. Let's put a asterisk. H2 plus I2 forms 2HI. Well, we know that's not going to be the answer. Why? Because A is just the same thing, but a simpler version. And remember, for a large Arrhenius pre-exponential factor, we're looking for an easier reaction. Okay, low means it's harder, essentially more difficult for the orientation to occur. For A, we have two atoms which don't need an orientation because they are simple. They just need to collide and they form their compound, right? So it's going to have a high Arrhenius pre-exponential factor. That's what you have to realize. Now, just by that logic, we should know that C is also not going to be the right answer. Why? Because it's a decomposition reaction. It's going to require a specific orientation. It's going to have a lower Arrhenius pre-exponential factor. And I can use the same logic for D. We're going to have a specific orientation collision between these two different elements and compounds. It's going to be a lower Arrhenius pre-exponential factor, and therefore we get A. Another way you can think about this is by realizing that A and B are so similar. One of them is designed to trick you, right? One of them is probably going to be the right answer. You can see that A is the simpler version, so the collision is going to be easier to occur in the right orientation, and therefore A is the correct answer. Okay, 32. Which reactions involve the transfer of a proton? Okay, so we have I, 2HCl plus Mg forms MgCl2 plus H2. Okay, so for this reaction, we can see the magnesium is being oxidized, and we have the hydrogen ions from HCl being reduced to form H2 gas. So we do see HCl dissociating to provide protons, but this is a redox reaction. It's not actually a transfer of the proton. So I would not classify this as correct. But we can always go back and double check. Now just from that, we can see that I is part of A, B, and D, so we know it's going to be C. But I'll just check the other ones just to be sure. So in this one, we can see we can see 2HCl plus MgO forms MgCl2 plus H2O. Now, the oxide ion from MgO in this case is acting as a base, and it's going to react with the protons from HCl, forming water. And this is just regular classic acid-base reaction, and it has a proton transfer. 100% that is going to be involved. So we know 2 is one of the right options. Now let's check 3. 2HCl plus MgCO3 forms MgCl2 plus H2O plus CO2. So here we have the carbonate ion reacting with the proton from the HCl. So the HCl is providing it to the carbonate ion, and that's going to form carbonic acid, which is going to be what decomposes into water and carbon dioxide. And this seems like another pretty standard acid-base reaction involving a proton transfer. So I would say it's definitely C. Seems like the only right option. I is simply not the transfer of a proton, while the other two are clearly transfers of a proton. So 32, we have C. Okay, 33. So it's an indicator question, okay? So the indicator HIND is used in the acid-base titration. So we have HIND forms H plus IND minus, okay? And it's asking us which statements are correct. So let's check it. In a strongly alkaline solution, color B is observed. Well, in a strongly alkaline solution, we're going to have a lack of H plus ions. And in order to replenish that, equilibrium is going to shift to the right. So it's going to move in this direction. That's going to result in a higher concentration of IND minus, which means color B is going to be observed. So that looks about right. I is correct. Okay. 2. Color A is observed when the concentration of H IND is less than IND minus. And this is a common mistake that students make, and I recognized it as soon as I saw it, actually, because look, so we have a higher concentration of IND minus. If there's a higher concentration of IND minus, you might think that the equilibrium shifts to the left, so color A is observed. But if you really think about it, high concentration of IND minus is just going to mean color B is going to be observed, because IND minus is essentially what brings about color B. So it's just saying that color A is observed when there's a lower concentration of HIND. That's just not true, because HIND is what shows color A. So if there's a low concentration of it and a high concentration of IND minus, it's going to be color B observed. So that is incorrect. Finally, number 3, IND minus approximately equals HIND at the end point. Yeah, that's how indicators work. At the end point, they should be roughly equal. That gives us I and triple I. Nice. Okay, 34. The overall reaction occurring at the electrons of a rechargeable metal hydride battery can be summarized as our metal hydride plus plus that forms our metal plus NiOH2. Okay. It's asking us which statement is correct. Okay, interesting. So the oxidation state of nickel does not change. Well, I mean, without even checking, I can tell it is changing, because you can see here, it is in the presence of the OH2, which has a charge of 2 minus, so it's Ni2 plus. Okay, this one is in front of this 2 minus and 1 minus, so 3 minus. It's going to be, this one's going to be Ni3 plus. So they're different. Okay, it does change. Okay, B. M is oxidized by the loss of hydrogen. That yeah, that's not true. Not really. Hard to see that. C. The oxidation state of one hydrogen atom changes from -1 to +1. Okay, yeah. So this is what I was looking for. That's the right answer, and the reason it's the right answer is because you might be wondering how the hydrogen atom can have a oxidation state of -1. Well, if you've read about your oxidation state, your redox, you should know there are some exceptions, some instances where the oxidation state of elements change. And in this case, when in metal hydrides, think about metals such as like sodium, right? It has a charge of 1 plus, right? Na plus. Okay, if we had hydrogen here and we had plus, it's not going to be neutral. So hydrogen actually becomes minus, okay? It becomes minus. So in metal hydrides, the hydrogen carries a -1 charge, and it's going to change to +1 in our products. That's going to give us C. I don't even have to check the last one, because it says the oxidation state of one oxygen atom changes from -1 to -2. That's just not true, and I know a C is right, so that is going to be our answer. Okay, in a redox titration, manganate ions are reduced to manganese ions, and iron ions are oxidized to iron 3 ions. Okay, iron 2 to iron 3, okay, sure. What volume in cm cubed of 0.1 mole per gm cubed MnO4 minus is required to reach the equivalence point in the titration of 20 cm cubed of 0.1 mole per gm cubed Fe2 plus? Now this looks really easy, right? We can just get the moles of Fe2 plus, and then we need to get the same amount of moles of MnO4 minus. We can just get the volume that gets us the same amount of moles, but that's assuming there's a 1-to-1 ratio, which it isn't. So what we have to do is, unfortunately, write out the entire equation. And so we need to write the equations for MnO4 to Mn2 plus and our equation for Fe2 plus to Fe3 plus. We gotta see what the ratio is. So let's do the MnO4 first, because the other one is very easy. So MnO4 minus forms Mn2 plus. Okay, so when you have to balance equations like this, redox equation like this, first things first, you have to look at if you have the same amount of your metals. So we have Mn, Mn. We have one Mn on each side, that's fine. Okay, next look at the O's. So we have 4 O's on the left. How do we get 4 O's on the right? Well, we use H2O. So we're going to add 4H2O. Now that we added 4H2O, you can see we have H's that are unaccounted for, so we add the same amount of H's on the left side. We add them as protons, hydrogen ions. So we have 8 H's to add, so we add 8H plus on the left. Okay, now that we've added that on the left, we can see the charges are the same, so we have to make the charges the same. So on the left, we have a charge of +7, and on the right we have a charge of +2. So we have to add electrons to balance them. So we have 7 on the left and 2 on the right, so we need to add 5 electrons, 5e minus, in order to balance the charges, and now it's 2 and 2. Okay, now let's look at our other equation. Okay, our other equation is going to be Fe2 plus forms Fe3 plus E minus. Okay, that's a much simpler one. Now to see what we need to do to it, well, if we wanted to combine the equations, which we don't actually have to, we just need to see what the ratio is, we would have to make the electrons the same as we could cancel them out. And the way we do that is by multiplying the bottom equation by 5 to get the same amount of electrons. So let's do that. We're multiplying it by 5. And just by seeing that, we're going to notice that the ratio of this is for every 1 of this MnO4 to Mn2 plus, we have 5 irons. We have 5 iron reactions. So the ratio is 1 to 5. So what are we going to have to do? Well, we know our ratio is going to be a 1 to 5 ratio. And now we can go right back into the question and just solve it using this ratio. So first, let's get the moles of Fe2 plus. So we have 20 cm cubed, which is 0.02 dm cubed, and we're going to be dividing that, multiplying that by 0.01, multiplying that by 0.1 gives us 0.002. Now that we have that, 0.002, divide that by 5, because remember, we have to account for the ratio. So we're dividing it by 5, and we get 0.0004. Now with 0.0004, sorry if it's messy, let's just make a section here. 0.0004. We have 0.0004. What can we do next? Okay, so we need to find the volume that will give us the equivalent. So essentially all we have to do is we need to divide this by our concentration in order to get the volume. Remember, volume equals moles over concentration. So we're just dividing by concentration. That's going to give us, it's going to give us 0.04 should be. Okay, and that's in dm cubed, but our answer is in cm cubed. Yeah, cm cubed, so it's 4. Okay, took a bit to wrap my head around that one, because a lot of writing, but yeah, pretty simple one as well. 36. Which statements explain the following reactions occurring in the upper atmosphere? Okay, chlorofluorocarbon compounds break down to produce chlorine radicals, but usually not fluorine radicals. So it's basically asking for the reasoning behind this. So let's check. So the CCl bond is stronger than the CF bond. Yeah, looks fair enough, because yeah, I mean that it's either one of these two, because this explanation it's not explained by the fact that the CN bond is stronger than the CCl bond. That's the opposite logic. We if it's able to break down to produce chlorine radicals but not fluorine radicals, it means the CCl bond has to be stronger than the CF bond. So there we go. So we know it's one of those two. So now we know a single chlorine radical breaks down many ozone molecules. We're looking at here now. So what's going to make it able to do that? Well, is it the chain propagation steps produce more radicals, or is it chain termination steps cause chlorine radicals to reform chlorine molecules? And it looks exactly like it would be this, because it's telling us that a single chlorine radical is able to break down many O3 molecules. It's not telling us about how it's able to produce more radicals. It's talking about how this single one is producing more chlorine molecules, allowing the process to recycle and reoccur, causing the more further breakdown of O3 molecules. There we go. Now, which term cannot classify ammonia? Well, nucleophile, yes. Ligand, yes. Bl acid, it can be classified as Bl acid. Oh yeah, Lewis acid is definitely not. It's not a Lewis acid. A Lewis acid is a electron pair acceptor, right? And we know that NH3 has no room for that, so it's going to be A. Which ions better leaving group in nucleophilic substitutions? We should just know this by doing paper 2's pretty common knowledge. It's going to be iodide ion, and the reason is for the weakness of the Ci bond. Remember that the weaker bond is going to be easier to act as a leaving group, and that's why the iodide ion is the best leaving group. Now, which statement is correct when 2-chloro-2-methylpentane reacts with water to form 2-methylpentan-2-ol? Okay, let's just draw this first. So 2-chloro-2-methylpentane, okay. Okay, so that's what it looks like. Should be. And it looks like we have a tertiary alcohol being produced, and it's going to be a tertiary halogenoalkane, so that's going to be SN1. Okay, so we're going to just think about all of these in the mindset of an SN1 reaction. Okay, water acts as a nucleophile and attacks the chlorine atom. Not true. Water does not act as a nucleophile, attacking the chlorine atom. The reaction occurs in a single step. Well, if it was SN2, it would occur in a single step, but this is SN1, a two-step mechanism, so not true. Carbocation intermediate. Perfect. Love to see it. That is correct. Homolytic fission occurs. Nope. It's heterolytic for this. And yeah, so it's C. And this is the last question. Wow. 40. Which illustrates the correct intermediate formed in the nitration of benzene by NO2+. I mean, end with a very easy one. For the intermediates, should know that for this reaction, the dotted line is there just by your knowledge, and that narrows it down to these two. And if you remember the mechanism for nitration of benzene, you should know that it's A. We have this positive charge here. If I remember the steps, I can draw it very briefly if you're unable to understand. It's essentially we have benzene and we're having this occur. We're having donation there, and that's going to make it into this intermediate where we have instability in this benzene ring, and we're going to have our NO2 attached here. And that's basically the mechanism. And yeah, this paper was pretty good. There are some parts I would say were pretty challenging, but overall not too bad of a paper. Yeah, hope you enjoyed that. It was quite a long video to record because I tried to explain everything. Sorry about the cuts in the video. There were times where either my Apple Pen was dying or people were walking into my room, and I didn't want to have that in the recording, so I just cut restarted a bit. But yeah, hope you enjoyed the video. Happy to do whatever paper you guys suggest me, and hope this helped because there's not a lot of resources for this new syllabus, so every little thing helps. So hope you enjoyed it, and I'll see you guys in the next one. Please like and subscribe if you enjoyed the video. Yeah, see you guys.